Good morning, everybody. Welcome to Tuesday morning of Chem 1211 with your host, me, Dr. White. I got a lot to do today because tomorrow is Wednesday, the day before Thanksgiving. By the way, before I forget, I hope all of you have a happy Thanksgiving and a happy Thanksgiving dinner, wherever you are. And what I like to do, hold on one second, I just see something that's bothering me. I'm back. But anyways, I hope you all have a happy Thanksgiving. Now, a lot to do today. Right after class today, I'll be sending out the email for quiz number 5. You'll have until tomorrow, I think 8 or 10 p.m. to finish quiz number 5. What I was saying before, since this Thursday is Thanksgiving, COD does not have classes on Wednesday. Therefore, I will not be having class or office hour tomorrow. But don't forget, after today's lecture, I'll be sending out the password for quiz 5. Now, as I mentioned yesterday, and let's go to Blackboard. All right. Does everybody see on your screen? Quiz number 6, important information. Waiting for my thumbs up, people. Thank you, Gianna. I posted this this morning, not too long ago, a week from tomorrow on the 30th, right after class. I'll be giving quiz number 6. And quiz number 6, you'll have until Wednesday. I've got something. You'll have until Wednesday, 11 a.m., 1st of December. Wow, where did this year go? To upload your answers as a single PDF file for quiz 6. And as I've mentioned this semester, I reserve the right to subtract 25 points from your quiz 6 total for anybody who doesn't follow instructions, meaning upload as a single PDF file, or who does not upload your answers on time. For some reason, Blackboard doesn't like me this semester, and the spacing for the next paragraph, when I upload it, it looks nice. And when I send it out, it looks not nice. But anyways, quiz 6 has 6 pages. It has 10 problems, including some multiple part, but no multiple choice. It's worth 55 points, which means there's 5 bonus points. It covers chapter 14 only, which includes Bronsted-Lowry acids, Bronsted-Lowry bases, chemical formulas of key acids and bases, conjugate acids and bases, water dissociation reaction, ionization constant of water, acidic solutions, basic solutions, neutral solutions, pH determination calculations, buffers, and titrations. That's a mouthful. And we'll finish that today. And as always, I'll get I recommend the day before the quiz, you download it. By the Sunday after the quiz, or earlier, I'll have your scores out. And also, I'll send out an email with your individual points. And the Monday after that quiz, I'll go through the answers in our Zoom meeting, but I will cut it out of the video. And if you can't come to a meeting, you can always come to my office hours, which I'll also have tonight, an office hour, or you can contact me and I'll set up a special private Zoom meeting. That's a mouthful. But anyways, that's quiz 6. So this weekend, have fun studying for quiz 6. Now, if we were face to face, I wouldn't be giving quizzes. My quiz 5 and 6 would be my test 4 if we were face to face. But because of the way they set up for the online active course file, I have to give only two. I can only give 2 tests, which I will, and also the rest are quizzes. So my hourly exams I normally gave during the semester, a couple of those I broke up into quizzes 1 through 6. All right, any questions about quiz 5 or quiz 6? All right, we got a lot to do, so let's get going. Yesterday, I started talking about pH. pH is equal to minus the log of the hydronium ion concentration. Remember, in brackets means concentration. H3O plus is the hydronium ion. Now, my gift to you this semester, if the hydronium ion concentration is equal to 1.0 times 10 to the minus x, then pH equals x. You don't have to take your calculator, find the log, then multiply it by -1. Dr. White knows how to do this, but since you're not going to be chem majors, which is okay by me, it's okay by you too, I bet, I'm giving you this gift. All right, let's do some practice. One thing I forgot to mention, I posted this morning in Blackboard, which I'll do next Monday, quiz 6 review and quiz 6 important information. And this would be important information that you'll get for quiz 6. All right, why don't you try this on your own? We've already done a couple of these, and I see a question. So, and Anna, alkaline, you can say instead of basic, it means the same. You're welcome. So it's your turn. What would be the pH of this solution if the hydronium ion concentration is 1.0 times 10 to the minus 10? And what is it acidic, basic, or you could say alkaline, but basic or neutral? You want to put down alkaline instead of basic? That works for me too, because I know what it means. Whoa, hold on. If you go back and look at my slide, I have that there. So when you're done, give me a thumbs up. Something while you're doing that. I don't have it on. Let me get something. Everybody see important information, which will be for quiz 6. How many people want me to do this and just get going on it? Give me a thumbs up if you want me to do it. All right, let me do this and then you can practice. And Monday, I'll be going through chapter 14 problem set, which you should work on over the weekend. So what are we trying to find? pH plus, is it acidic, basic, or neutral? What are we given? This. What are we given in important information? pH equal minus the log of the hydronium concentration. And if the hydronium ion concentration, H3O plus, is equal to 1.0 times 10 to the minus X, then the pH is X. So given that information, which is also over here, I can now say pH equal minus the log of the hydronium ion concentration. We found out it's that. And since it's 1.0 times 10 to the minus X, X is 10, so the pH is here 10. Now, what you have to learn, and it's an important, it's in the test quiz 6 review, is the following chart. And you should need to memorize this. There, I've cut way down on the memorization, but this is one you should memorize. And you could have also written alkaline for basic. All right, well, the pH is 10. 10 is above 7, so that means it's basic. And let's go through this again. What is the pH? We're trying to find that. We're given this, the hydronium ion concentration. From important information, you're given the pH equal minus the log of the hydronium ion concentration. We put that number in. My gift to you this semester, if the hydronium ion concentration, which in this case is 1.0 times 10 to the minus X, then the pH is X, which in this case, X is 10, not minus 10. pH is always between 0 and 14. And you should learn this little table or chart that at pH 7, it's neutral, below 7, it's acidic, above 7, it's basic. All right, let's do another one, or I'll do this one. Oh, let me change this slightly. All right, 10, yep, 10 points. If the hydroxide OH minus concentration is 1.0 times 10 to the minus fourth, then what is the pH of the solution? And is it acidic, basic, or neutral? Ooh, 10 points, that's a lot. So what are we being asked to find? pH. What are we given? The hydroxide OH minus concentration 1.0 times 10 to the minus fourth. And now I say, oh, I know, pH equals minus the log of the hydronium concentration. Wait a second, we don't have this. We have this. So what do? Well, you need 2 steps. First of all, step 1, we have to find a hydronium ion concentration. Well, how do you do that? Well, if you look at important information, test quiz number 6, notice the ionization constant, Kw, named after me, not really, but it feels good, is the hydronium ion concentration times the hydroxide equals, and that should be 1.0, equals 1.0 times 10 to the minus 14th. So I now know this, and I can use it, and I will. So we know this. We want to solve for this, so we need it alone on one side. Remember, anything divided by itself equals the number 1. But whatever I do to one side, I have to do to the other. This cancels out. I'm left with the hydronium ion concentration equals 1.0 times 10 to the minus 14th over the hydroxide, which we learned from the problem, 1.0 times 10 to the minus 4th. If I do the math, and this I can do in my head, because the exponents, powers of 10, this would be now 10 to the minus 10. So step 1, you have to calculate using the ionization constant, Kw, no, not me, I wish it was, but that to solve for hydronium. Now we want to find the pH, and therefore step 2, calculate the pH. And how do we do that? Well, important information, quiz number 6, and let's take a look at it, make sure Dr. White's not lying to you, and he's not. pH equal minus the hydronium ion concentration, log of that. And if the hydronium ion concentration is 1.0 times 10 to the minus x, then pH is x. So pH is minus the log of the hydronium ion concentration, which in our case, we calculated right here. In this case, X is 10. So like the last problem, I didn't plan it that way, but this came out. The pH is 10. And as you learned the last problem, anything above 7 is basic, 7 neutral, below 7 acidic. So let's go through this. And because I'm rushed for time today, on Monday and Tuesday, I will come back and do these problems, this specific problem again. So unlike what I normally do, I'll just do one of these. If I have time today, maybe I'll come back and do a second one. But I promise next Monday and next Tuesday, I'll do this type of problem again. 10 points, you better believe I will. But we're trying to find a pH. We're given the hydroxide ion concentration, but the pH is minus the log of the hydronium ion concentration. You need 2 steps. First one is calculate hydronium ion concentration. And you do that by using the water ionization constant, Kw. That's not me, but it would be nice if it was. OH minus concentration times H3O plus concentration equals 1.0 times 10 to the minus 14. We want to solve for hydronium ion concentration. Therefore, to get rid of hydroxide OH minus, we divide by, because anything divided by itself equals the number 1. And whatever you do to one side, you have to do to the other. And I did. And now we can rewrite it. Hydronium equals, this comes from that. I should have really written this. This, and then we know what to put in there. And then we get that number. And then second step, calculate the number, the pH, because we have now the hydronium ion concentration, H3O plus. And here we have pH minus the log of the hydronium ion concentration. And then we put that in. X is 10, because it's 1.0 times 10 to the minus x. pH would then be X. In this case, 10. Is it acidic, basic, or neutral? You should know this chart. 0 to 14, pH. Below 7, acidic. Equal to 7, neutral. Above 7, basic. And 10 is above 7. And that's how you do it. Like I said, normally I'll do more than one, but today, because I'm want to finish everything today lecture-wise, I only could do one, but Tuesday and Monday and Tuesday, I'll do this again. Not this one, but different ones. All right. wrong thing. Now, you should remember pH is from 0 to 14. The lower the pH, the more acidic it is. The higher the pH, the more basic it is. And this is a logarithmic scale. And we did our pH practice time. In the book, you have POH. I've never used it, never. So I'm going to skip it. Now, acids and bicarbonates, see board. And you did this in last week's lab, I believe it was with the airbag, or 2 weeks ago. By the way, with Chandler's principal lab, and I'll mention it later, normally would be due today because one of your colleagues asked me. I had postponed it till I think Saturday or whenever. I'll have to look. I might even postpone it till next Tuesday. All right. Oh, I know where I was going. I lost my train of thought. If you have any acid and you react it with sodium bicarbonate, this is called a neutralization reaction, acid base, because it's an acid, any acid, and you should know sodium bicarbonate, and you should know its structure is a base, and what you get is a salt plus water plus carbon dioxide. And since I don't have time today, next Monday, I will tell an amazing story about the first chemical reaction I ever did with my hands. I was about 5 and a half. My father taught me this, and it was way cool. But you're going to have to wait till Monday. All right, before we do acid-base titration, let's do another important problem. All right, why are you being? I'll be done shortly. All right, everybody see the problem on their screen? 2 points each. If the pH of, thank you, Gianna. If the pH of a beaker of water is 7.0, then what happens, and this is important, so let me get my important thing. What happens to the numerical value of the pH? I'm not asking for a number, but what happens to the numerical value of the pH if you add a few drops of concentrated NaOH, sodium hydroxide, and in a second step to beaker water at pH 7, if you add a few drops of concentrated H2SO4. Now, the first thing you have to know is sodium hydroxide is a base. And you also have to know, well, Dr. White can't draw a straight line today. Hold on. Well, that's better. pH 14, 0 to 14, 7. 7 is neutral. Below 7 is acidic. And above 7 is basic. So if I add base to it, sodium hydroxide, it's going to make it more basic. So what's going to happen to the pH? It will increase. Whenever you add a base to a solution of water, the pH will increase, go closer to 14, depending on how much you add. Now, you need to know H2SO4 is an acid. And when you add an acid, you're making it more acidic, and therefore the pH will decrease. Now, if you wanted up here, you could have put an arrow up. Down here, you could have put an arrow down. Either one would work for me. So whenever you add a base, the pH to water at 7, the pH will increase, get higher. Whenever you add an acid, and you should know sulfuric acid, H2SO4 is an acid, the pH will get lower. Now, there's a very important concept, which you're going to be learning in today's lab, which is why I wanted to get through it, called acid-base titrations. And that's a neutralization reaction in which, and I'm never going to ask you on a test, what's the titration, acid-base titration? But that's an acid or neutralization reaction in which a measured amount of volume of acid or a base of known concentration is completely reacted with a measured volume of acid or base of an unknown. And this concentration and the acid-base titration allows you to determine the unknown concentration, which, in case you forgot, is, if I can spell it, molarity. And what this means is the following reaction. I have an acid and a base, and they're both strong. The equilibrium is essentially going to be this side, and you'll get this salt. And this is called the neutralization reaction. And you can measure when, say, you're doing unknown acid and a known base, when you add all the base and all the acid is reacted, there's a way of determining visually how that happen or when that happens. How is that determined? By using an indicator, which is also, Dr. White will probably always say, a pH indicator. And a pH indicator is a compound that has two different colors depending on is the environment it in acidic or basic? Again, an indicator, a pH indicator, exhibits different colors depending on the pH. And the most widely used indicator is called phenolphthalein. And phenolphthalein changes color at 7.0. It goes from clear to pink or wine colored, depending on how you call your colors. My sister says, you don't know your colors. Well, I know red, green, and blue. But when it gets to the fancier ones, well, I sort of know them. So what you do is use this molecule, and the pH changes the structure, and that structure changes how it absorbs light. And that I'll never ask you. And titration data are used to calculate molarity of an unknown acid or base with a known acid or base solution. Now, when it comes to titration at neutral pH 7.0, when phenolphthalein changes color, you can calculate the moles of a known molarity acid or base. And based on the neutralization reaction, you can determine how many moles of the unknown molarity acid or base was present in a volume of sample of known volume of sample of the unknown acid or base, and therefore calculate the molarity of that unknown acid or base. And right now, if you're saying, what's going on? Hopefully you didn't hurt your head by going like that. Let's go through it again. And I just said, if you know the volume of the unknown, the moles, you can calculate the molarity. Now, here's important things to remember. When you have the change in your indicator, which is called the titration endpoint, moles of base equal moles of acid. When you reach the endpoint, when the indicator changes color, moles of acid equals moles of base. So let's look at a special gift from Dr. White. When you have a monoprotic acid or base, which is all we'll use in this course, notice that in special information, important information, quiz 6, at neutralization, that's when the indicator changes color, moles of acid equals moles of base. For monoprotic acid, which you only see in base, you can simplify it, and I could, if you need to, I can show you how you derive this, but I'll just give it to you. And that is milliliters of acid times molarity of acid equals milliliters of base times molarity of base. And both sides would have 1,000 that cancels out. So you can come up with this simplified concept. Now, if I look at the clock, I'm going to do something a little differently. It's a little odd now, but let's call 9:42 by this clock. And let's come back in 5 minutes. This is a good time to take a break. We'll do titrations. I have one other thing buffer, and we'll do the lab. And I think I'll have time to go back and do another pH problem after we do a couple titration problems. So let's take a 5-minute break. Come back at 9:47. I can get up and stretch. See you in 5. Oh no, I'm late. Let's get going. And in case I forget, which I shouldn't, remember, have a happy Thanksgiving, everybody. Oh, that calls for this. Have a happy Thanksgiving, everybody. All right, let's get back to work. We're talking about titrations. At neutralization, the moles of acid, that's not what I want. At titration, at neutralization, that's when the indicator changes color, the pH indicator changes color. We know moles of acid equal moles of base. And I'm giving you this simplified equation that you can use. This will be important information, quiz number 6. And that's milliliters of acid equals the molarity of acid times equal that. Let me do that again. Milliliters of acid times molarity of acid equal milliliters of base times molarity of base. So let's do a titration problem. All right, let's go through this. If you have to, by the way, thumbs up, people. Do you see 10 points on your screen? Thank you, Gianna. All right. If you have to add 125 milliliters of a 1.63 capital M NaOH solution to make the color change in 175 milliliters of a HCl solution, then what is the molarity of the HCl solution? So first of all, what are we being asked to find? Molarity HCl. What are we given? We have 125 milliliters of a 1.6, remember capital M is molarity, NaOH solution. We're also given, we have 175 milliliters of the HCl. This is a titration. How do you know? When you're working with an acid and base, sodium hydroxide base, HCl hydrochloric acid and acid, and you're trying to find the molarity of one, it's a titration. And if you look at important information, quiz 6, At neutralization, when the solution changes color due to the indicator, moles of acid equal moles of base, and milliliters of acid times molarity of acid equal milliliters of base times molarity of base. So let's go back to our problem. We know in a titration, we know at color change, which is called the endpoint, moles of acid equal moles of base. And that's milliliters. Let me try that M again. Milliliters of acid times molarity of acid equals milliliters of base times molarity of base. And now this is my acid. So I have 175 milliliters of acid times, I don't know yet, the molarity of the acid. I'm laughing because it's the worst A I've ever written. I gotta fix this. That's better. Equals milliliters of base. Here's my base. So the milliliters is 125 milliliters NaOH times the molarity is given right here. And now we want to solve for molarity of acid, which is HCl. And what I should have done, and let me go back and correct it. Okay. And now how do you solve for this? Well, you get it alone on one side. And anything divided by itself equals the number one, cancels out. So if I wanted alone on one side, I'll divide by 175. See what happens when you rush, you make mistakes. Even I do. Slow down, Dr. White. Well, whatever you do to one side, you have to do to the other. And this cancels out. So we're left with the molarity of the HCl equals 125 milliliters NaOH times the molarity of NaOH, sodium hydroxide base, divided by the milliliters of the acid. Now, for this, forget about the unit or the actual chemical, but notice milliliters cancel out and you're left with a molarity. And now I will grab my calculator, turn it on, clear it. 125 times 1.63, whoops, and then divide that by 125, 175. And my calculator gives me this number. I'm laughing because you'll see why. This, but remember on quiz 5, I'll have it today when you take it, and quiz 6 will have it. Underneath your name, it'll say, please use proper significant figures for all calculated answers. And even though I don't think for quiz 5 you don't need it, please use all atomic weights to 3 significant figures. Well, this is 3 significant figures. This is 3. Uh-oh, he's in his rut again. 3, and this is 3. So we have to round this off to 3, keep the 1, keep the 1, keep the 6, use the 4 to round off. That's 4 or less. So I can drop all this. So the molarity of the HCl solution is 1.16 molar HCl. And this is something that's done in the chemical industry and also in academic labs and research labs all the time. And this is also where you have an unknown whatever, and you have to determine the molarity of that. So let's go through this again. If you have to add 125 milliliters of a 1.63 molar NaOH solution to make the color change in the 175 milliliters of the HCl solution, then what is the molarity of the HCl solution? And we're trying to find capital M HCl molarity. That's an acid. We're given an amount of base NaOH and the molarity used to change the color of the solution, and we're given how much the volume, 175, of the HCl solution. And once again, this is a titration. When you're asked to determine the molarity of something by mixing two things together, an acid and base, titration. And in the past years ago, students would have to memorize this, but being the nice person I am, don't tell anybody about that. But I will give you important information. Quiz 6 at neutralization. That's when the color of the pH indicator changes color. Moles of acid equal moles of base. And here we next have milliliters of acid, and this is only true for monoprotic, monobasic acids and bases, but that's all used in this course for you. And that's mils of acid times the molarity of acid equals milliliters of base times molarity of base. In a titration, you'll always be given the milliliters of acid, the milliliters of base. And if you're trying to find for the acid, you'll be given the molarity of the base. If you're trying to find the molarity of the base, you're given the molarity of the acid. And that's how you do it. Oh, let's do another one. These are fun. We got time. Oops, I almost started writing cursive. I still like to do that, but you guys, most of you can't read it. All right, let's take a look at this. If it takes 135 milliliters of 7.835 capital M HCl solution to make 375 milliliters of a KOH, potassium hydroxide solution change the color of the pH indicator, then what is the molarity of the potassium hydroxide KOH solution? So what are we trying to find? Molarity of KOH. You should know this is a base. What are we given? Well, it takes 135 milliliters of a 7.835 molar HCl solution to make a change. And also you were given, you have 375 milliliters of the KOH solution. And this is a titration. Whenever you're trying to find molarity and you're given an acid and a base, this is a titration. And for today's lab, later today, when we get to it, you'll be doing a titrations at home when you do that lab. And because it's a titration, important information at neutralization, when the solution changes color, moles of acid equal moles of base, and that means milliliters of acid times molarity of acid equals milliliters of base times molarity of base. And this will be given to you. In the past, you'd have to memorize this. So at neutralization or at color change, we know if you remember molarity, when you have milliliters and molarity, you can calculate moles. Well, that's how I derived this, but I'm helping you out. Now, remember, KOH is a base, hydrochloric acid. Surprise, it's an acid. So I can now put in, right down here, my milliliters of acid is 135 milliliters. My molarity is 7.835 molar HCl. For my base, my milliliters is 375 milliliters KOH, potassium hydroxide, and my molarity, KOH, is what we're trying to find. And now to solve for molarity of KOH, we want that alone on one side. So when two things are multiplied, remember to get rid of one of them, anything divided by itself is number one. So to get rid of this, I'll divide this side by 375, the same number. If I can write it. But whatever you do to one side, you have to do to the other side. This cancels out. This leaves me molarity of KOH equals 135 milliliters divided by, or times 7.835 molar HCl divided by 375 milliliters KOH. You don't have to do this, but I will. I'll rewrite this because I like to do that. And notice milliliters cancel out. I'm just left with molarity. And now I can pick up my calculator, clear it. Hold on, I did something wrong. And my calculator gives me this answer. But this is 3 significant figures. Ooh, 4 significant figures and 3 significant figures. And remember, when you're multiplying and dividing, you get the same number of significant figures in your answer as the number that has the fewest significant figures. So we should get 3. Keep the 2, keep the 8, keep the 2, use the 0 to round off. That's 4 or less. So the correct answer is this. And that's how you do titrations. Remember, the key is at color change, moles of acid equal moles of base. And my gift to you this semester, instead of having you figure out how to do this, it's milliliters of acid times molarity of acid equals milliliters of base times molarity of base. And that's how you do a titration. Now, throughout the industrial world and even the academic and research world, we do a lot of titrations. And by determining the endpoint of how much acid or base is present for certain reactions, you can find key parameters called specifications or measurements for things that you make. And that's standard in the chemical industry. One company I worked at, Unichem Chemicals, I came in as I was hired as the laboratory manager for all North America. And first thing I did, I saw they were doing titrations in a very old way called what's called using a burette. Everybody see the burette on your screen? Let's see if this brings me a bigger picture. See right here? And it has the measurements on there, just like you would see on a graduated cylinder. Right here, this valve is called a stopcock. And by turning it, you can control how much acid or base you're adding slowly till the color changes and measure the volume. And then knowing the molarity of what's in the burette, you can determine the molarity of, or the amount of acid or base and whatever you're titrating. Now, this is old school. It's good in teaching labs But in industry, when I came on, I saw they were using burettes, and I said, that's why we're having a quality problem. And what I did was I learned about it at another company. Everybody see on your screen on the right, it says dosimet titrator. This you can control to 0.002 milliliters. It's extremely accurate. It's extremely expensive. Back in, I hate to say this was back at about 1989. I came into the Unichem lab. I said, we need some of these. And back then they were 5,000 a piece. And then I also was able to work with the company to set up what's called an auto titrator. Because every morning my chemist in the QC lab did about 100 titrations, which took most of the morning. And by setting up some of them with auto titrators and also other with manually using the dosimat, it was quicker, much more accurate, better quality products. There's one problem though. The research director in the Netherlands, when I did this, he had a number of PhD analytical chemists trying to solve what I did. And he got really mad at me, really mad, because I did what he couldn't have his people do, just Dr. White. And later on, that got me fired because he was really bad for years at me. That and a couple other things I did that he was really mad because people were saying, wow, this guy's pretty good. And I think he felt threatened, thought I'd get his job for worldwide lab manager. And if he hadn't fired me, I might have. But anyways, that's in the past. All right, let's move on because we got to do a lab today too. All right, last thing I want to talk about in this chapter is buffers. And buffers are a solution. This is important. Hint, you should know this, just like titrations. And a buffer solution is a solution that resists major changes in pH when small, and that's important, small amounts of acid or bases are added to it. Now, I'll never ask, but buffer solutions are an acid and its conjugate base of weak acids. So when you have a buffer solution, if I add a small amount of a weak acid, a small amount of a weak acid or base, the pH doesn't change or hardly change at all. It stays essentially the same. And guess what? Your blood is buffered. That's what keeps you alive by keeping that pH very narrow range. And other things in your body and in life, other things we use in the chemical industry are buffered, meaning it's a buffered solution. And let's do one quick problem. I'm almost done. All right, let's look at this. 2 points each, or it could make it 3 points each. What happens to, and again, key, the numerical value of a buffer solution, and that's very key, at pH 6.8 if you add a few drops of a dilute acid solution. Well, buffer solution by definition resists change in pH if you add a small amount of acid. And dilute and a few drops means a small amount. And the answer is stays the same, or I could have written down doesn't change. Now, what happens to buffer solution, numerical value of a buffer solution at pH 6.8 if you add a few drops of a dilute base? By definition, buffer solutions resist change in pH if you add a small amount of acid or a small amount of base. And adding a few drops of a dilute solution, base solution, is a small amount. And the answer here also is stays the same. And that's buffers. And because we don't have class tomorrow, I've rushed a little, but we'll cover more, go back and cover some of the stuff again. And I'm done with this chapter. What that means is I finished the material for quiz 6 a week before quiz 6 next Wednesday. Not tomorrow, next Wednesday, a week from tomorrow. And on Monday, besides going through the answers for quiz 5, which when I'm through today, I'll send out the email so you can take it and you have until tomorrow night to hand it in. I will be going through the quiz 6 practice problems, and I'll do quiz 6 review. Well, we got a lot to do next week, but we'll get it done. And then Tuesday, I will do some more practice problems for quiz 6 because I rushed through a couple today. Now, it's lab time. Wow, time flies. I'm looking at the clock when you're having fun with acids and bases. Wrong thing. All right, what's happening here? I see what happened. That was open and I couldn't close it. All right, hang on 1 second. Sorry about the delay. All right, everybody see, and let me make it smaller. Determination of acetic acid, which is the concentration in vinegar using titration. And what you're going to be doing is determining the molarity of acetic acid in vinegar. And let me remind you, So I've got to open it. All right, that's the right whiteboard. Everybody see my whiteboard on their screen? All right, vinegar, and this is acetic acid. And vinegar is acetic acid and water. So you should be able to, if you have vinegar, which your kit does, what is the molarity of acetic acid in vinegar? And what you're going to be doing is the following reaction. You're going to take acetic acid and react it with sodium hydroxide solution. And this is an acid-base reaction, and you'll make, this is called sodium acetate. It's a salt. Plus water. And you'll be using a pH indicator. Phenolphthalein, which when it's acidic, it's clear. When it's basic, the solution, it's pink. I like calling it a wine color myself. I guess it matters what wine you're drinking. A red wine. And so if you start out with a solution, unknown solution of acetic acid, and you add slowly a known volume of a known molarity NaOH solution, when the solution goes from clear to pink, you know you've neutralized all the acetic acid. And at that point, you'll know, depending how many milliliters of acetic acid times the molarity. Well, hold on. Of acetic acid equals the milliliters of base that you add times the molarity of the NaOH solution, which you're given. And what you're going to be calculating is this number right here. So if I divide both sides by milliliters of acetic acid, and this cancels out. So what you're going to be doing today is this calculation. And you'll calculate using a syringe how much milliliters of NaOH you have to add to make it turn pink. And just briefly, and I'm going to show you a video in a second, not of me, but a video of it. You'll know how many milliliters you pour out from the vinegar bottle. And you'll be doing that in an Erlenmeyer flask. Erlenmeyer flasks were designed to allow stirring while you do a titration. Let's go to here. Let's go here. Oh, guess what? I never turned my
Today we're
speaker on.
going to do a titration of vinegar. So we have 5% vinegar solution. We have our distilled water. We have
All
a
right, I'm going
0.1
to
molar
go forward and notice
will disappear. And notice it.
now this solution in the Erlenmeyer, they have a bigger one than you'll be using, has the vinegar, a known amount, plus a few drops of phenolphthalein. You're given that. If you don't, you put in the phenolphthalein, guess what? It will never change color. Important thing. Students make this mistake when we do this face to face. They'll say, Dr. White, I've added my base to the vinegar and it's not changing color. And I asked, did you put the phenolphthalein indicator in there? You got to put a few drops. You've got a little bottle. You only need about 2 or 3 drops, and then it will change color. And what do we mean by changing color?
It clouds up a little bit, but if you swirl that around, it will go clear because phenolphthalein is clear in an acid solution. And now we will begin the titration process by adding some sodium hydroxide to our acid solution. You will notice that we are going to start seeing pink, and as we swirl it, the pink will disappear. So we will add it at a little faster rate. See the pink forming, and we'll swirl it and we'll notice the pink goes away. And our job as we titrate is to bring it to a point where the pink color holds, even though you may swirl it. So I'm going to slow down this process now, and we will just go a few drops at a time. We don't want to go too fast because we don't want to go past what is called the end point. The end point is where the pink color stays. And
Titrations are practice of patience.
What you'll start to notice is that the pink color stays longer and longer. You notice that the pink drops along the side of the beaker where the splashing occurs remain that pink color as the phenol, and I'll bring this closer to you. What we have there, see, still not quite, we still have clear, full drops going at a time. There we go. Still clear.
Now watch, see how it stays pink? Just then, that's what you, stop. You went a little too
And that
far.
is the end point of our titrate.
And that's what it should look like. Now, in today's lab, you'll be doing the same thing. You'll need your Erlenmeyer flask and the different things they show here. And you'll need a syringe and a vinegar. And in your kit, you'll find a sodium hydroxide solution and the phenolphthalein indicator. And generally, either behind or underneath your Erlenmeyer, put a piece of white paper so you can see the color change better. And you'll follow the directions in activity 1, dispense 5 milliliters using your eyedropper of the, and record the mass and record the volume. Then you'll take the vinegar and pour it into your Erlenmeyer flask. Then you'll add 2 or 3 drops of phenolphthalein solution to the vinegar. Now it says at this point, take a photograph. You don't have to. Then from the 10 milliliter bottle, and you have 1 molar, and call it 1.00 molar NaOH, put it in a small cup and fill the syringe. And then very slowly, you'll put a little in at a time till the color changes. Now, when you're adding a little at a time, you have to swirl this. The guy in the video, gentleman, being polite, he was going like this. Now, Erlenmeyer's, watch the wrist action. That's many decades of doing titrations. If I had $1 for every titration I did or managed, boy, I'd be a millionaire, maybe, but a lot. All right. And what you'll do is keep on adding until the color changes and stays changed. You don't want to go until it's super dark. Just as soon as it changes to that pink color and stays that, you stop. At that point, I'd like you to take a step 13, take a measurement. Next, at that point, initially you saw the volume of the syringe like at 0 or 0.1. And when you're done, you'll be able to measure what's the volume left in there, and the difference is the volume of the NaOH. And then what you should do is dump it down the sink and rinse it a couple times with water. If you have DI water or bottled water, that's better. And then you'll do the same thing twice. Actually, they have here 3 times. And you'll fill in this initial volume, the volume. You can find the mass of the vinegar. And what I'm going to do, I didn't have time today, but before Saturday, I will, and hopefully I'll do it correctly this time, I'll put out a calculation sheet how to do the stuff for this lab. Now, in real life, in the chemical industry, when you're doing a titration, you always do it in duplicate. Here you're doing it in triplicate. You could use the practice. Now, for activity 2, you'll do the same thing, but instead of the vinegar from your bottle in the kit, find some vinegar in your house. But I'd highly recommend do not use balsamic vinegar, because the dark color will be harder to see color change. Now you can use apple cider vinegar, champagne vinegar, or the regular white vinegar it's called that you have in your house. Now here, where I have it doing it 3 times, do it 3 times. And then, now activity 3, omit. And I'll put that on Blackboard today sometime. Activity 3, omit. And with that, do the lab. I've modified the lab, so stuff on pKa I cut out because I'll be honest, I've been in the chemical industry many decades, and the areas I worked at, we've never used pKa. I'm sure there's some that do, but for everyday life and use of titrations, you don't use it. So I'm not going to have you do it. Shh, don't tell anybody. And with that, I'm done for today. Not actually. Later tonight, I'll have my office hour. If you need help, in about 5-10 minutes, I will send out the email for quiz 5. You have until tomorrow evening to hand in your answers, upload them for quiz 5. The lab we did last week is not due today. I gave you some extra time. This lab is due next Tuesday. And with that, I'll say, have a happy Thanksgiving. Have a great rest of the week. I'll see you either tonight, Tuesday, or next Monday, because there's no class on Wednesday, and we don't have class on Thursday or Friday anyways for this class. And I'll say, happy Thanksgiving. Gang gesund. Goodbye. I stole that from Beverly Hillbillies.